In this last video, we've got a ball that's growing at a rate of 0.8 centimeters per second. The radius is 6.6 centimeters. How fast is the volume changing? So we got a ball, the ball is growing at a certain rate, and we can tell, what we'll be able to do is see how fast the volume is changing based on how fast the radius is changing. And this is going to be really cool. Let me show you how we do it. First, we need our volume equation, which is 4/3 pi r cubed. That's the equation for volume, 4/3 pi r cubed. Now, what we need to do is we need to find, we want to know how is the volume changing as the radius is changing. This, by the way, is called a related rates problem. If you want to do some Googling or search for it on Bing or DuckDuckGo, this is a related rates problem, and so that's the kind of category of this problem. So we can relate the variables v and r, but we want to relate the rates, and we do that with an implicit derivative. V dv dt is equal to, we take the derivative of this. 4/3 and pi are a constant, so they just come along, and the derivative of r cubed is 3r squared. Now, remember, we're taking the derivative with respect to time, so I need to write dr dt. That's it. That's our entire derivative. dv dt equals 4/3 pi 3r squared dr dt. The 3 cancels and something amazing happens. So here's our formula. dv dt equals 4 pi r squared dr dt. Now, do you recognize this formula? This formula is actually the formula for the surface area of a volume. Isn't that incredible? It makes sense that the rate of change of a sphere growing, the rate of change of it growing would be equal to the surface area of it, because we're just adding on surface area to make the volume grow. In the same way, look, on another note, here's the area formula of a circle, pi r squared. Notice that the circumference formula is the derivative of the area formula, 2 pi r. The 2 just comes down. Isn't that great? So the rate of change of a circle growing, its area, is we're just adding on more circumference, and that makes the circle area get bigger. So that's one of the things I love about calculus is a lot of these geometry formulas are connected by a derivative, and it was in front of our face the whole time, and we never noticed it. Anyway, I'll get back on track with this problem. The rate of change of the volume is based on this rate of change of the radius, and so now we just need to plug in our values. It's growing at a rate of 0.8, and the radius is 6.6. So the 6.6 we put in for r, and the rate we put in for dr dt. It's really important that you don't mix these up. That's the value of the radius, that's the rate of the radius growing. Throw it in your calculator. 4 times 3.14 times 6.6 squared times 0.8, and we get our answer, which is approximately equal to 437 the book says 0.9, I get 0.7, so I probably should have done more values for pi, but we get an approximate answer. And that's it. That's a related rates problem. As you can imagine, this goes much more into greater detail with many more examples, but we'll stop there for now. I hope you enjoyed this chapter. I really hope you enjoyed the connection between the area and the circumference of a circle is just a derivative, and there's a lot of other fundamental geometry connections like that as well. So I hope you're enjoying these videos. If you have any questions, please contact me, and I will see you in the next chapter.